Hello, good morning. Assalamualaikum warahmatullahi wabarakatuh. In today's presentation video, we will be explaining the combustion analysis in engines or fuel burning efficiency. I am Salsa.
I'm Alifa.
I am Noel.
I am Arga.
And I'm Zaha.
On to the first slide.
So what is combustion analysis in engine? Combustion analysis in internal combustion engines focuses on understanding how fuel burns inside the cylinder to produce power, making it an essential topic in mechanical engineering. It involves studying the chemical and thermal reactions that occur when hydrocarbons react with oxygen and examining how efficiently this reaction converts fuel into energy. Engineers measure factors such as air-fuel ratio, temperature, pressure, and the composition of exhaust gases to evaluate combustion quality. This includes analyzing CO2, O2, CO, and unburned hydrocarbons, NOx, and exhaust temperature to determine whether the combustion is complete or if harmful emissions are being produced. Complete combustion releases the maximum amount of energy from the fuel and mainly produces CO2, making it a key indicator of engine efficiency. Why combustion analysis in engines matters. Combustion analysis is essential because it allows engineers to improve the overall performance of an engine by optimizing how fuel burns. By understanding the combustion process, engineers can increase fuel efficiency and power output while minimizing harmful emissions such as carbon monoxide, nitrogen oxides, and unburned hydrocarbons. It also helps identify and prevent engine knocking, which can damage engine components and ensures that combustion remains complete, stable, and consistent under different operating conditions.
Key concept of combustion analysis. Understanding combustions require knowledge of the ideal air-fuel ratio, known as the stoichiometric ratio, which ensures complete combustions. Engineer also analyze whether the mixture is a rich or lean, because rich mixture produce more power but higher emission, while lean mixture improve fuel efficiency but can lead to misfires. Managing this balance is crucial for achieving optimal engine performance. Now, there are three examples of combustion analysis in engine. The first one is complete combustions. When a gasoline engine burns octane with enough oxygen, it produces CO2 and H2O only. This means the fuel is burned fully, giving maximum energy output and high fuel efficiency. The second one is incomplete combustions. If the air-fuel mixture is too rich, not enough oxygen, the engine forms CO, carbon monoxide, soot, and unburned hydrocarbons. They show poor combustion quality, wasted fuel, and increased pollutants. The last one is exhaust gas indicator. Exhaust analysis showing high CO and low CO2 indicates incomplete combustions, means the engine is not using fuel effectively. Meanwhile, high CO2 and low CO signals good combustion efficiency.
Next. Next is the measurements in combustion analysis. To analyze combustion, engineers measure cylinder pressure, combustion temperature, and the composition of exhaust gases. These measurements provide insight into how much heat is being released, how evenly the fuel is burning, and whether pollutants like carbon oxidant or NOx or unburned hydrocarbons are forming. Sensors such as pressure transducers and gas analyzers are used to collect this data.
Combustion analysis in engine reaction. So here we got the reaction find is C C plus O2 equals 2 and 2 8 CO2, which is C8H18 burns with exact oxygen needed. It produces only CO2 and HO2, which is considered maximum efficiency and zero pollutants. However, rarely happens in real engines due to imperfect mixing, aeration, and timing. Real engine produces just the main product H2O, which is cheaper, C combustion, unburned fuel, hydrogen, and oxygen. Because and H2O is combustion, and highest Hc plus NOx equals to poor efficiency or high temperature, used to evaluate and improve engine performance and emission. Next slide is the combustion efficiency. Combustion efficiency indicates how much of energy is actually heat. Engineers calculate it by comparing the actual heat released to the theoretical maximum. Higher efficiency achieved through proper air-fuel control, correct ignition timing, good fuel atomization, and consumption.
Modern engines use advanced technologies to improve combustion quality. Systems like electronic fuel injection and gasoline direct injection precisely control the fuel delivery, while turbocharging increases air supply for better combustion. Variable valve timing and engine control units adjust timing and mixture dynamically. Exhaust treatments such as catalytic converters and EGR systems further reduce emissions. So in conclusion, combustion analysis is essential for developing engines that are efficient, powerful, and environmentally friendly. By studying how the air-fuel mixture burns by using measurements such as temperature, pressure, and exhaust gas composition, engineers can determine how effectively fuel is being converted into energy. This helps to optimize ignition timing, air-fuel ratio, and fuel delivery to improve performance and avoid issues like knocking or incomplete combustion. Modern engine technologies apply these insights in real time, which allows engines to run smoothly while reducing fuel consumption and emissions. Overall, combustion analysis enables engineers to create cleaner, more reliable engines that meet modern performance and environmental standards. That's it from our group. Thank you for listening.
Thank you for listening. That
Thank
is
you
all
for
from our group.
listening.
Bye. Love you.
Bye, guys.